Okay. So welcome to our series of lectures on Higgs mechanism. The last class we worked out that what's the kinetic energy and the potential energy of field may be. The kinetic energy, as we have discussed, that the kinetic energy of electric field, energy density of electric field is proportional to the square of the electric field. So just like electric field, the square of the electric field gives us the energy density, potential energy density. Similarly, if we have a field, say phi, the potential energy of that, potential energy density of that field must be proportional to phi square. Now for the kinetic energy for a particle of mass m is given by half mv square, where v is the variation of the position with time. So it's the square of the position, variation of the position with time. So we can say that the kinetic energy is proportional to v square, velocity speed, where v is the variation in the position with time, the square of that. Similarly for the field, because the field does not depend only on the time, it not only varies on time, it varies both on space and time. So by the same argument, the kinetic energy for the field must be like this. If the field is phi, it's a variation of the field with respect to time square minus, so minus is due to the relativity, because we know that in the relativity we have any event can be written as like this, s square, any event square of this event is c square, c the speed of light, c square t square minus x square minus y square minus x square. Similarly here, the kinetic energy for the field will be the variation of the field with respect to time as well as with respect to the space. So this is the time part, variation of the time part. This is the variation of with respect to x. This is the variation of with respect to y. This is the variation of with respect to z. But we write it in a more compact way. But it looks like something like funny. By writing, I am writing it is like d mu phi, where here mu is subscript, this is superscript. Where d mu phi means variation of phi with respect to, x mu here. And d mu phi means, so this is actually where mu is an index. It's 0, 1, 2. 0th index is reserved for time, and these are for space, x coordinate, y coordinate, z coordinate. So here this is actually d phi by mean d phi by dx. So the kinetic energy for the field is will be written like this, it's proportional to this. It's not simply the square of this not and not d phi by dx mu or mu square. Because had I been written like this, this means if I write it like this, say del phi by del x mu square, means this is del phi by del x0 plus del phi by del x1 plus del phi by del x2 plus del phi by del x3. So since mu runs from 0 to 1, 2, 3, But this we have to obtain like this, and here it's minus sign, it's not minus sign here, it will be plus sign. So that's why it's not written like this, it is written like this. One subscript, then superscript. And we will discuss why we are writing like this. Okay. So our aim is to understand why we write a vector like this, a mu, and not simply a mu square. In tensor, in relativity, wherever you encounter relativity, you find that one of the components written as subscript, the next one is superscript. So a vector in a three-dimensional space, coordinate space, simple rectangular coordinate space is written as A is written as AX I plus AY J plus AZ K. Okay, where I, J, K are the unit vectors directed along the increasing direction of x, y, and z coordinates. X-axis, y-axis, z-axis. So the I will be along the increasing direction of the x-axis. This is I unit vector. This is the j, and this is k. Where I is tangent to the x-axis as well as perpendicular to the base formed by the YZ plane. Similarly, J is parallel to is tangent to the y-axis and is perpendicular to the plane formed by XZ plane, XZ coordinates. Now, if you multiply, suppose this by, say, dot product I, you will get here AX I dot I plus AY J dot I plus AZ K dot I. Now, since these vectors, unit vectors, are orthogonal, this will result in 0, this will result in 0. Why? Because J dot I will be 0, K dot I will be 0, I dot I will be 1. So the x component of this is the projection of A along the unit vector I. So this is there. Similarly, if you multiply it by J dot product, you will get this one, multiply, and by K dot product by K, we will get the Z component. Now this is simple in case of rectangular components. Now if you suppose we have a coordinates which is curvilinear in nature. Yeah, in curvilinear coordinate system. Suppose you have a coordinate system U1, U2, U3. These are the coordinates. Now, yes, sir. As you want right here. It's just for making drawing easier. Now, the unit vectors along the increasing U1 will be tangent So this is the unit vector here, denoting like E1. But there is maybe another unit vector which must be perpendicular to this U2, U3 plane, and suppose that unit vector is perpendicular, so this is. Now this unit vector will be written as superscript, where this one was written as subscript. And this one unit vector is called covariant and this is called contravariant. So we have two sets of unit vectors here in this case. In earlier in orthogonal coordinate system, this I is tangent as well as perpendicular. Here the tangent one is and perpendicular one are different. This is the tangent one, this is called covariant and this is called contravariant. So E1, E2, E3 are called the covariant base vector. Base. And E1, E2 are called contravariant. Base vectors. So any vector can be expressed either in terms, you can express either in terms of covariant as well as in contravariant terms. Suppose we have a vector A. So the vector A can be represented either in terms of, so if we represent it in this base, we have to write like this: component and if you want to write in this, on this base vector, the same vector can be written as A1, A2 plus A3. Oh, sorry. Oh, sorry. Remember that one of the component, one is superscript, next one is subscript. So these are called contravariant components, these are called covariant components. So the contravariant components are expressed in terms of covariant base vectors and covariant components are expressed in terms of contravariant base vectors. Now, okay. Now we see the rectangular coordinates, three-dimensional. We have written as vector A as AXI plus AYJ plus AZK, where the mod of A, the square of the mod, will be given by AX square plus AY square plus AZ square. But here we cannot write like this. If you worked out, you will get that's not equal to. It's not equal to A1 square plus A2 square plus A3 square. Also, you cannot write it like this. Not only you can write, but you will not get result, accurate result. If you want to, but if you take one component contravariant and one component covariant and multiply, then that will be correct. So the mod of A will be correct only when we multiply one component covariant, one component contravariant, plus one component covariant, one component contravariant, one component covariant, one component contravariant. Okay. If you want to study more about this, you can go through my series of lectures on relativistic quantum mechanics. Quantum mechanics. Masroor lectures. Relativistic quantum mechanics. And the first few lectures we have discussed these things. So if you want some more, you will get here from here. Masroor lectures, relativistic quantum mechanics. Okay. Now suppose this is the vector A. I am writing it like this. This can be written as AK, EK, where K runs from 1 to 3. I am not using the summation here because we know that the repeated indexes are summed over. This is called Einstein's summation convention. That wherever the indices are repeated, it means they are summed over. Assume that they are summed over. So it's already summed over. Now if you multiply it, as we have seen in the rectangular coordinate system, that is AXI, AYJ plus AZK. If you multiply unit vectors here, A dot I. You will get AX I dot I will be one other. So the X component is here. Similarly, if you multiply here by say EJ, here you get EK. Now this EK, EJ is written as this is the jth component, as here it's the X component. So it is jth component. It is given by K, J, and this GJK, GKJ is actually EK dot. Now the same vector can be written as like this also. The same vector A can be expressed as A1, B1, A2, E2, A3, E3, or AK. Now if you multiply here by, say, EJ, you get AK, EK dot EJ. This again written as J, K, J, AK, and this is this component, and this is here G, K, J, is EK. Now, in case of relativity, we have that here you will find that this G, K, J is a matrix. It's 1, 0, 0, 0, 1, 0, 0, 0, 1. Similarly here also. One zero 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 1 0 0 0 1. Substitute here, you will get but jth company. But in case of relativity, we have here minus. First component is plus, and the all others are minus. So that this metric changes. First component is positive, then all other components will be negative. So I will do like this. In relativity, we write it like this: A mu G, or say mu A mu. Why we are taking as not J and K? Because in relativistic, mu and nu represents 4 components, where I, J, K represents 3 components. Mu or nu represents 0, 1, 2, 3. Similarly, A nu will be G mu. And here in this case, G mu is a matrix which is 4 by 4. First term is 1, 0, 0, 0, 0, minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. So if you work out, you will get the first component as A1, A0. The next component will get minus AX. Mu will be 1, that will be AX, then minus AY, then minus AZ. So that's why we used to write we are used to write one component as covariant and another component as covariant, contravariant. So the potential energy for the field will be phi square by 2, and kinetic energy is proportional to, and kinetic energy for the field I am taking field as a phi phi, this as written as del mu phi, when del mu means phi means del phi by del x. So it's del mu. One comes as covariant, one other is as contravariant. So the Lagrangian density for the field will be kinetic energy minus potential energy density. So this is the kinetic energy minus potential energy density. And kinetic energy is given by this potential energy proportional to phi square. So this will be written like I am taking phi square here, not phi, mu phi, not mu, because here we have considered as a scalar field. Had it been a vector field, this will be vector, because we know that the gradient of the scalar becomes vector, so that's why it's written as like this. It's not here. But if had it been a vector field, suppose this is another vector field, say A, so we will not write like this A square. Then in that case we will have to write A or A. Because now we have considered scalar field, so so the Lagrangian density, the kinetic energy is half variation of the field with space and time. So it is del mu phi. This is the variation with respect to both time and space. And minus half m c square by h phi square. Now if you use, we have already studied the Euler's Lagrange equation for the field, and that the Euler's Lagrange equation for the field was del by del x mu this our we have derived it, already derived this equation, Euler's Lagrange equation for fields. So if you apply this is the equation of motion for the fields. So if you apply to this Lagrangian, you will get suppose we are taking the first one. So it is delta L by delta phi. Delta phi is here. So if you distribute your different n c square by h cross. Now we'll take this one. This will be differentiated. Here it is delta phi by delta x mu. It's again delta phi by delta x mu, because this is delta mu is delta phi by delta x mu, and delta mu phi is delta phi by delta x mu. If you multiply, worked out, this will be delta phi by delta x naught minus delta phi square of that, and delta phi by delta x 1 whole square minus delta phi by delta x 2 whole square, and so on. So if you, if you take its derivative, the square part give it, finish 1 by 2, and you are left with simply delta phi by delta x mu, or you can write simply as now take this one. Derivative of this part. The derivative of this part means that's phi 1 or so this, for this we obtained this result, and for this part we have obtained. Substitute here, you will get and this minus minus makes plus m this is similar to our wave equation. This is similar to the simple harmonic motion. D square x minus dt square plus omega square x. Where x is the position which varies with time. Here, the field which varies with both space and time. So it includes both space and time. And this is omega square here, and this is the field. So now, bit by bit, we have come across this, how the fields and the language of the field and the field. Now, in the next class, we will maybe start with fields. We have three types of fields: Fermion fields, Boson's field, and Higgs field. So we worked out about those fields. Okay, for today.